Great pleasure to have a chance to give a talk here, and I would like to thank the committee organizer, the organizing committee, for inviting me. And the title of my talk is Solvability of Dirac equation and geometric applications. I'm sorry, there's a typo in the title. Geometric applications. And I will talk about the Dirac equation. And on the two-dimensional case, we can control the solvability of the Dirac equation by a curvature integral. And in the non-compact case, we will prove by homogeneous method that the Dirac equation in two-dimensional case is always solvable. And on compact Riemannian manifolds, we will give a new proof of Bayes result about the first eigenvalue of the Dirac operator. And on non-compact case, we will talk about the Riemannian manifolds with cylindrical ends. This kind of manifolds arise from the localization procedure. Usually, we have to solve some kind of PDE on a punctured Riemannian manifold, and around the puncture point, we give the manifold a cylindrical Riemannian metric, and after solving the PDE, we have to group the solutions. So in this case, we have to control the solution. And I think most important is that we have to consider Z2 grading structure, that is half Dirac. Because on compact Riemannian manifolds, Dirac is self-adjoint and elliptic operator. So its index is 0. So we cannot use the Dirac to produce useful invariance. But instead, if we consider half Dirac, I mean if there is a Z2 grading structure, then we can find some useful invariance by half Dirac. And finally, we will talk about the applications to holomorphic curves and extenders in G2 manifolds. Let's start with some basic notions. Let Mg is a Riemannian manifold, and dimension is n, and we define Clifford bundle is the quotient bundle. It's a quotient of the vector bundle of tensor algebras by the ideal generated by such elements. V square is a norm square defined by the Riemannian metric, and here the dot is Clifford multiplication. A Dirac bundle is a vector bundle on which there is a natural Clifford left action satisfying these two conditions. The first says that any unit tangent vector acts defines a unitary action on the fiber. And the second is the Leibniz rule. On this equality, the dot means the Clifford action, and the connection. This connection is the connection on the bundle S, and this connection is the Levi-Civita connection on the tangent bundle. And we know that by definition that Levi-Civita connection on this, the tangent bundle induce connection on this quotient, because the Levi-Civita connection preserves this ideal. So on Dirac bundle, we can define the Dirac operator by the connection and the Clifford action. Let's look at some examples. The first example is given by the D bar. If M is just the Euclidean space of dimension 2 with the standard metric, in this case we know that the Clifford algebra is C2 and the Dirac is given by D bar equation. The next is in the 4-dimensional case, M is the space of quaternions, and in this case the Clifford algebra is the matrix, the 2x2 matrix, and S is given by the Dirac sum of two pieces of H. And in this case, Dirac is given by D bar Q and D bar and DQ. And even in the study of quaternion analysis, this operator is quite important, because if you want to generalize the notion of analytic function to quaternion case, we have to use the Cauchy-Riemann type operator. It's a main difficulty to generalize complex analysis to quaternion analysis. And if the underlying manifold is a spin manifold, then the spin representation gives us the Atiyah-Singer Dirac operator. But the underlying manifold to be spin manifold, we know that the existence of the spin structure has topological obstruction given by the Segner-Whitney characteristic class. But the existence of Dirac bundle, there is no obstruction. For any Riemannian manifold, we can define the Dirac bundle in this way, and the Dirac operator is given by the Hodge-Durham operator. So in this case, the Dirac is square root of Laplacian operator, the Hodge Laplacian operator. So if we want to solve the Dirac equation, the solutions of the homogeneous equation are called harmonic spinors, because on compact manifolds D is self-adjoint, so the solvability of the Dirac equation is equivalent to the vanishing of harmonic spinors. A result due to Lichnovich says that if the manifold is compact and a spin with positive scalar curvature, then the homogeneous equation only has trivial solution. That is the vanishing of the harmonic spinors. So we can always solve Dirac on compact spin manifold with positive scalar curvature. But this condition, I mean the curvature condition, is not always necessary. And we can see this from the following. Qingchun's theorem says that if two matrices are conformally equivalent, then we have the relation of the corresponding Dirac operator. Here is S. Here psi is the bundle isomorphism. So the corner of S, the corner of Dirac and the Dirac prime are the same. So the solvability of D and D prime are the same. But we know that the positivity of scalar curvature is not preserved by conformal transformation. So in general, we want to relax the pointwise scalar curvature condition. We want to fix some notations. In the Bochner formula, I want to introduce the notion of R. R is given by the curvature tensor. It's given by the curvature tensor and the Clifford action. In the spin manifold case, R is given by the scalar curvature. So Lichnow's theorem is an easy corollary of the above formula. It follows from integration by parts. And then we also introduce the lower bound of this operator. It's a self-adjoint operator. And we also introduce half Dirac in the following way. If S is orientable and even dimensional Riemannian manifolds, there is always Z2 grading. Z2 grading means that we have parallel decomposition. Parallel means that we use a connection on S. And this decomposition respects the Clifford action. And then we see that in this case, the Dirac operator splits in this way, and the curvature operator splits as this. We see that in our previous examples, here is actually the half Dirac, and this is a half Dirac. And Hijazi and Bayes' theorem says that if S is a Dirac bundle, a compact Riemannian manifold in the two-dimensional case, if the genus is 0, that is, M is exactly sphere as a topological space, and D is a classic Dirac. Classic Dirac means that we use the spinor structure. Now then they have the estimate of the first eigenvalue. It means that we can always solve the Dirac, the classic Dirac, and we have a control of the solution by this estimate. And in higher dimension, this result is due to Hijazi. Hijazi obtained the lower bound of the first eigenvalue by the first eigenvalue of the Yamabe operator. In non-compact case, we don't have. As far as I know, there is only one existence result due to Gromov and Lawson. It says that if M is a complete Riemannian manifold and S is a Dirac bundle over Mg, if the curvature is bounded from below by a positive constant, then the Dirac operator is always solvable in L2 space. Now, this is our result. The first says that if Mg is a two-dimensional Riemannian manifold, and suppose there is a C2 function, and C2 function comes from a homogeneous estimate. If there is L2 function phi satisfying this inequality, and in the compact case, if this integral is finite, then we can solve Dirac and we can control the solution by this estimate. In the non-compact case, we can show that we can construct the weight function to make sure this integral is finite. So we can always solve the Dirac in L2 locally in local L2 space. So to compare with Bayes' result, we know that our result implies the lower bound of the first eigenvalue of Dirac. So in particular, if this integral is positive, then du is the Dirac is always solvable in L2 space. And even if we look at the classic Dirac, then this curvature is given by the Gauss curvature. So by using the Gauss-Bonnet formula, we know that this inequality is equivalent to Bayes' result. This comes from the Euler number of sphere. So, in the Z, if we consider the Z2 grading, then this condition will imply the solvability of the half Dirac. And as a corollary, we know that on non-compact surface, the Poisson equation is always solvable because the Laplacian D has a square root, which is given by Dirac. The next result states that in higher dimension, we can improve Hijaz's estimate of the first eigenvalue. And actually, this improvement is not important, but the proof is quite different. Hijaz used the ingenious method to complete square to get the estimate. This is an optimal estimate. So their proof is quite ingenious, but from the point of view of homogeneous L2 estimate, it's quite simple. Only takes a few lines. And just as I mentioned before, we can recover Bayes' result in the spatial case by using the Gauss-Bonnet formula. And on non-compact Riemannian manifold, we have the following. Let Mg is a Riemannian manifold with cylindrical ends. Riemannian manifold with cylindrical ends means that there is a manifold, and outside a compact subset, it looks like a cylinder. It has a cylindrical metric, Riemannian metric. I mean, this part is isometric to some B tensor R. And B is a compact Riemannian manifold of codimension 1. It's isometric to the product of these two Riemannian manifolds. And suppose there is a compact subset such that outside the compact subset we have the lower bound of the curvature. And then the result is that there is another constant, positive constant beta with the following property. If the curvature is bounded from below by minus beta. This is a negative constant on the compact part. Then we can solve the half Dirac, solve Dirac in the weighted L2. And this is the exponential L2 space, and it's exponential Sobolev space. And actually, we don't know how small this constant is, but you can take beta is 0. So if the curvature is non-negative on K and positive outside K, then we can solve the Dirac. And the exponential space is defined by the integration with exponential phi. And the exponential phi outside m minus k is given by a linear function tau. Tau is a linear function in this direction, in the cylindrical direction. And this is a standard space used in symplectic geometry. Now let's look at some applications. The first is about the holomorphic curves. Let sigma be a holomorphic curve in a Kaist manifold, and in this case, we denote the normal bounded by n, and Dirac is given by d bar and d bar star, and the Dirac bundle has Z2 grading structure as this, and this is S minus. So by our solvability criterion, we know that if this integral is positive, then sigma is Friedhelm regular. Friedhelm regular means that sigma is automatic transversal. A curve is said to be transversal means that if we study the moduli space of holomorphic curve representing a given holonomic class, then the modular space near this given curve have a smooth manifold structure with dimension given by the half Dirac. So and we compare with some knowing result. The first is Hoffer's result. It says that if we look at the holomorphic curve in a four-dimensional symplectic manifold, then Hoffer's result says if the Chern number of the normal bundle is bounded below by 2G minus 1, G is the genus of the curve, then this curve is Friedhelm regular. And this is actually a corollary of our criterion, because in this case S is the normal bundle times the cotangent bundle of sigma. So the lambda is given by the curvature of the normal bundle and the curvature of sigma. That is the C1 number of the normal bundle and the Euler characteristic number of sigma. And this is a 2 minus 2G, so we recover this condition. So in this sense, we generalize Hoffer's result to higher codimension, because we do not require the dimension of X to be 4. So sigma has higher codimension in X, but but we require the manifold is scalar. This is Hoffer's result. X is only symplectic. It's different. And the second result, the second is compare with we can compare with Markov result. If the curve is given by S2, in this case we know that the normal bundle splits into the Dirac sum of holomorphic line bundle. And Markov's theorem says that if the first Chern number of each line bundle is bounded from below by -1, then the curve sigma is Fredholm regular. And this is also follows from our result, because in this case the curvature is given by the R is given by the curvature of the bundle S, and now the S splits into line bundles. So the curvature tensor splits into the Dirac sum of the curvature of each factor. So we recover this theorem, and our result generates the automatic transversality to higher dimension and a higher codimension and a higher genus, because in Markov's result she requires that the genus is 0, and in our case there's no condition on the genus of the curve. The next is about the instantons in G2 manifold. G2 manifold is a 7-dimensional Riemannian manifold with endowed with parallel cross product, and an instanton A is a submanifold calibrated by the cross product. And their theorem says that the normal bundle of the instanton has the structure of Dirac bundle, and the deformation of the instanton is governed by the Dirac operator. So we can use so our result about the eigenvalue, first eigenvalue, can give a criterion of the rigidity of the instanton in G2 manifolds. So, and this condition is not clear because it's a first eigenvalue. So you can look at a special case. If the normal bundle has positive curvature, then the first eigenvalue must be positive. So in this case, A is rigid. And this is what we want to do. We want to generalize the result from holomorphic curve to J holomorphic curve. Let X be a symplectic manifold with compatible, almost complex structure, which is not integrable in general. And for J holomorphic curve, we can consider the linearized operator. In this case, the operator is given by L0 plus alpha, and L0 is a complex CR operator, but the difficulty comes from the alpha. This term is a real linear, not complex linear. And we are going to generalizing our corollary about the holomorphic curve to the case where G is not integrable. And there is some evidence that we can't expect topological condition like a trinomial condition in higher dimension and higher codimension and a higher genus case for the automatic transversality of pseudo holomorphic curves. Now I will talk about sketch the proof. We will consider the L2 space, the weighted L2 space, and we introduce the weighted adjoint of Dirac, and the basic a priori estimate is given by this one, and it's a corollary of the Bochner formula. But the difference is that we have the weight function here, and it's similar to homogeneous estimate for Debye equation. The point is how to choose the weight function from geometric assumptions. This proposition looks complicated, but it's a solvability criteria. We want to find some function phi satisfy this condition, and this integral is finite. If we can find phi satisfying these two conditions, then we can solve Dirac with estimate as these. So to prove our theorems, we want to produce weight function. The first is in two-dimensional case. In two-dimensional case, this condition 6 reduced to the following, reduced to this one, and if the manifold is compact and this function is positive, then this must be finite. So in this case, we only have this condition, and this pattern disappears in this case because n equals to 2. And it's easy to see that to find the existence of such a function phi is equivalent to the integral is positive. So that is why we have the criteria. So this is the first result. And in non-compact case, we can always find the exhaustion function to make sure the corresponding integral is finite. So we can solve Dirac in two-dimensional case. And in higher dimension and a compact case, we can to make sure to guarantee this function is positive, we use eigenfunction to produce the weight function phi. And the last one is given by the last one is about the cylindrical case. The cylindrical case, to produce the weight function phi, we first solve Dirichlet boundary problem to get the first eigenvalue function. It means that it's this is a cylindrical. This is a manifold with cylindrical ends, and we first solve the Dirichlet problem in this part to produce the function eta. Produce function eta. Eta is the first eigenfunction here. And the nodal set theorem says that the first eigenvalue function must be positive or negative. So we choose the positive first eigenvalue function. And then we construct the function h here by a linear function, because this is a product manifold given by this submanifold and the line. So in this direction we have the linear function here, and use a cutoff function rule to group these two functions to produce the weight function. And it is easy to see that this function phi satisfies the condition 6 and condition 7. So we can solve Dirac equation on manifolds with cylindrical ends. And our result comparing to Gromov and Lawson, we see that we do not require the curvature is positive in the compact part, but here the curvature is required to be positive, to be bounded from below by a positive constant alpha. So it's a difference. So I think I just stop here, and thank you for your attention.